Hi, my name is Tom Brown. I'm the director of Borderland Sciences Research Foundation, and here we are back again in our secret lab hidden in the vast suburban wastelands of Southern California. Today we're with scientist Eric Dollard, who's going to explain to us longitudinal electric waveforms. Now, the modernistic science of today will tell you that longitudinal electric waveforms do not exist, and we're going to show you that they do. And here, basically, to get a practical demonstration or a practical analogy, we have water, and everybody understands the waves in water, which we can call a transverse waveform, standard waveform. And we know standard waves as they go along in the water, and the movement of the water is up and down, just like we know a boat on the water will go up and down, and the energy flow goes in this direction. So a transverse wave, we have a phase quadrature between the movement and the energy flow. And here we have longitudinal waves. And a longitudinal wave could be like a tidal wave or a tsunami, which we know is undetectable till it hits the shore. So as it goes through the water, the movement of the water is linear and the energy flow is linear, so we see it's in phase conjunction in the direction it goes. In the boat on the top will receive no up and down motion from that wave. And to get a more practical demonstration here, Eric Dollard will demonstrate. We have here a piece of BX cable, and I'll just act as the ground on this.
Okay, to start with, our transverse wave, which will be our quadrature motion, will be represented by this form. As we can see, we have an exact analogy to what's drawn on the board. If I transmit just one pulse, you can kind of see it takes a long time to get to the other end. But the longitudinal wave, of course, is over there almost immediately, and other than the slippage at the other end, it's almost undetectable that this wave even exists, other than that little shaking around. But it's slower. There we go. See, there's really not much motion up and down or around, but it's there right away. As soon as I move my hand, the other end responds. Where in this case, it takes a very long time to get there. So this serves as a very practical analogy of these two types of waves. Okay, as to carry our analogy further here, if we drop a stone in the water, we'll produce both types of waveforms in the water. Now we know the transverse waves form concentric rings which propagate out. But the longitudinal waves, which are not normally seen, of course, travel as straight lines in the depths of the water, which are indicated by down this way. Now this also happens to be the electric field around one wire, or what's called electrical conductor. Now if we look over in the other page here, we see when we start having a system of conductors, then the field changes, and we can have either the transverse motion of electrical energy, which moves into the paper, or in other words in the directions of the wires, which these are being the cross sections of the wires, or in a transformer, energy is conveyed longitudinally from primary to secondary conductors. So we have again our two types of fields here, representing longitudinal and the transverse, which of course is hard to represent because it goes into the paper. And again, these things are at right angles to each other. The longitudinal is going that way and the transverse is going this way. Okay, these lines that we see on the paper that we've represented with our wave fronts, in actuality around this system of conductors, represent what are called the dielectric fields of induction and the magnetic field of induction. Now in general, the magnetic fields of induction are concentric rings, as indicated by the dark lines here. Dielectric field of induction are usually radial lines, as indicated by the dotted lines. So in general, the dielectric field is conducive to the transmission of longitudinal forms of energy, and the magnetic fields are conducive to the transmission of electromagnetic or transverse forms of energy. So we might say that our transverse waves are called the electromagnetic waves, which has become the standard terminology, but our new waves, or longitudinal waves that we're dealing with here, are called longitudinal magnetodielectric waves, in contradistinction to the existing form of the electromagnetic or transverse electromagnetic waves. This book by Steinmetz here is a good source of reference to prepare one for the study of these types of electric induction. Here's the title page here for those who'd be interested in finding out more about this stuff. This book is quite old.
1914.
Is written as an explanation for another book that Steinmetz wrote on the theory of electric waves, which is extremely complicated. But this one's quite simple and will render information to the electrical engineer that completely change the outlook on electricity. In our study of electric waves, we're going to start with the well-understood transverse electromagnetic wave, and we're going to do some measurements here to determine the characteristics of such waves. To start with, we'll have a radio frequency generator and a step-down transformer to drive a long section of coaxial cable, and then a high impedance bridging voltmeter to measure the rise of electric potential due to resonance at the distant end of the cable. Now we'll go over to our test setup here on the bench. And we have our radio frequency generator and our transformer, which is a little toroidal core inductance. And then we have a roll of just regular coaxial cable and the high impedance voltmeter. Now what's going to happen here is a series of impulses, alternating electric impulses, will be produced by the radio frequency oscillator and launched down the cable with a finite propagation velocity. These impulses will travel around in the cable, reach the open circuit at the end of the cable, turn upside down, and reflect back, and again be delayed and return to the oscillator. When the impulses of the oscillator frequency are such that they match the time of propagation delay produced by the propagation of electricity down the cable, when this inverted impulse comes back from reflection, the oscillator has gone through 1/2 of a cycle, and it also is producing an inverted impulse. So these two inverted impulses add, and a double impulse goes back down the cable, turns right side up when it gets reflected, comes back to the oscillator. The oscillator has gone through another 180 degrees of shift and is producing a right side up impulse to match the reflected inverted, or now right side impulse. And this process keeps on going on and on until the voltage rises to a level where the losses of the system prevent any further increase. So what we're going to do is we're going to sweep the frequency here and find the resonance point of this cable to determine propagating velocity. Now, as you can see on the voltmeter here, we have a definite peak. So I'm swinging an oscillator. If we go to roughly our half voltage points, we find we have a bandwidth of about a few hundred kilocycles roughly. And it peaks out at a frequency of almost precisely 2200 and 20 kilocycles. So what we'll do next is we'll plug this into our equations and determine the speed at which our impulses propagate on the coaxial cable. In reviewing our test data for our transverse electromagnetic wave of electric induction, for a TEM coaxial cable RG62, which is the cable type we use, transmission impedance 93 ohms, total length of cable 2,750 centimeters. Full wavelength of this piece of cable then would be 11,000 centimeters, since it's a quarter wave resonance and you have to multiply the length by a factor of 4. Now, based on the velocity of light, frequency of quarter wave resonance for a propagating velocity equaling that of light, the frequency should come out to 2727 kilocycles per second. The actual frequency we measured was 2,220 kilocycles a second. Now if we take the ratio of these two velocities, we find that the propagating velocity along this cable was 81% of the velocity of light. Hence, this transverse electromagnetic wave is a retarded wave in that it propagates at a velocity less than that of light. Now, the reason for this retarded propagation velocity is due to the fact that the velocity of light is slowed down by the translucent medium that fills the cable to insulate it, and the resistive losses and conductive losses of the cable in general also tend to slow down the wave a little bit. Now what we're going to do next is go to the longitudinal wave and show our test setup, do our measurements, and perform our calculations on this wave. Okay, now we have our longitudinal wave test set up. Again, we have the same generator. This time our transformer couples the generator energy to the first turn of the coil, which is wound of very fine, fairly fine wire. And then we have a capacitive probe pickup to measure the voltage rise at the end of this coil. And at the neutral end of the coil, we have a large capacitance plate to produce our impedance dissimilarity, so we end up with a quarter wavelength rather than a half wavelength resonance on this coil. Now we'll look at our test setup again here. And we have, of course, the same generator as before. And then focusing in on the coil here, we see we have a primary turn, which loosely couples to the secondary, or the actual coil itself, through the first turn here, and then the rest of the coil pretty much engages in a free oscillation. And then our capacitive pickup is just a clip lead clipped on to the so-called insulating part of the coil. So we have a very light coupling between the end turns here and the probe wire, which of course goes to our same voltmeter. So what we'll do is we'll sweep around with the oscillator again and find out what kind of resonance characteristic we have here. Now we notice a difference right away. The resonance of this type of wave is much sharper. Rather than varying over several hundred kilocycles, now I'm varying over several kilocycles. So we're talking about a sharpness factor, or a Q, of 100 times greater. Now our frequency lands roughly 3,400. We're in between two marks on the dial here. We'll say 3,400 kilocycles per second. Now we'll go to our mathematics and compare this with the other wave and get into our velocities and frequencies and what have you, so we can study the character of this wave. Okay, covering the test data here for a longitudinal magnetodielectric wave. Our LMD wave structure was a Tesla extra coil. Transmission impedance of this was 4,200 ohms. Wire length, again, is 2750 centimeters to make it analogous to our roll of coaxial cable. And again, the full wavelength would be 11,000 centimeters. 4 times 2750. So the frequency of quarter wave resonance for a propagating velocity of this length equaling to that of light would be 27 kilocycles, such as before. Our actual frequency measured, of course, was 3,400 kilocycles per second. So taking our ratio of frequencies or velocities gives us a velocity of 126% of the velocity of light. Hence, this wave is an accelerated wave. So we've broken the speed limit of the velocity of light. Or you might say we might get a ticket from the relativity police in this case. At any rate, going back to our structure over here, we can see how this occurred. Is we're really not having transverse flow between the turns anymore, but the energy is now spiraling due to the complex quantities of induction along the wires in this direction. So we have a spiraling wave around the coil, and this gives us an effective velocity exceeding that of the velocity of light. And this shows a very fundamental error in many texts which give the method for calculating the resonant frequency of a free oscillating coil or a Tesla coil as being related to the velocity of light. So clearly we have to develop a new system of equations to describe this. Now what we're going to do next is build up a system of analog computers where we can study these waves a little better. With the coaxial cable, obviously we'd have to cut the cable open and stick probes inside to make measurements. In this case, focusing in on the voltmeter, when we use the longitudinal resonance structure, the thing is very sensitive, as you can see on the voltmeter, to any type of changes around it. So if you try to get in there to measure it, you can see by me bringing my hand near the coil that a definite shift out of resonance occurs in the meter. And as an example, I'll keep my hand very close to the coil and find the new resonance peak, and it's gone down about 30 kilocycles just by bringing my hand within 3 inches of the coil. And of course, I bring it away, I have to rehunt for the new resonant frequency. So we'll show you how these waves exist in their analog form, and Tom Brown will give you a brief introduction on the relation between the analog computer and the digital computer, and why we have to use analog computers for the study of these waves. And this will constitute part 2 of this videotape.
We hear the word computer quite often these days, but there's actually 2 types of computers. The computer that most people understand is a digital computer, and it's a very effective machine for certain functions. I use it quite extensively in the management of borderland sciences for database management and word processing. We find it in relationship to the study of transverse and longitudinal waveforms. It has very little use. And we can compare the 2 types of computers here. In digital computer, which of course is silicon chips, we have numerical functioning only. In an analog computer, which is a network built up of coils, capacitors, and various physical things, we have physical functioning as well as numerical. In the digital computer, we have no measurement of function as possible, while in the analog computer, we have direct measurement possible at any point. So you can stick probes in there and find out what's happening at all different sections of the waveforms, where you can't do anything like that on the digital. The mathematical form of the digital computer is dissimilar to that of the wave under study, in fact somewhat inimical to it, and the mathematical form of the analog computer is identical to the wave under study. It's an actual structure in space representing what the wave is. And the digital computer cannot be connected to actual operating electrical system directly, but an elaborate interface must be employed. So you're not really getting a direct relationship between what you're doing. Its interconnection must be used. While analog computer can be directly connected to the electrical system and thereby perform operation upon actual waves. So we find in the analog computer that it's an actual tool for the studying of these waves, and a very promising laboratory tool. And now Eric Dollard will give a practical demonstration of analog computers in the study of transverse and longitudinal waveforms.
In our analog study of electric waves, we'll start with an element of what we've been working with, which should be one pair of wires. And we'll call this the element of transmission, a differential element, as indicated by this symbol here, of an elemental length, which either be 1 centimeter, 1 inch, 1 foot, or 1 light year, depending upon what you want to take as unit length. So this is a little slice of the transmission section. This can be a little cut out of 2 wires of the coil, or it could be the center wire, this being the shield around the coax. The direction of longitudinal flow in this element will be in this direction, and the direction of transverse flow of this element will be in this direction. And we can see these 2 flows occur at right angles to each other. And in the case of the Tesla extra coil, they'll perform a complex addition, and we'll end up with a spiraling wave going up around the coil. Okay, now our analog of the magnetic field of the wires can be a pair of inductance coils, filter chokes or radio frequency chokes or transformer coils, or anything that has the ability to store and return magnetic energy. The analog of the dielectric field will be a pair of capacitors. And these can be any form from mica to oil, depending upon exactly what you want to do. Now when we combine these 2 together, then we have the analog of the complete transmission element. And in either case, the energy can go this way or it can go this way. And we have one element here of our analog transmission. And we have some radio frequency inductance coils of 10 millihenries, and we have some high Q pulse capacitors of 0.047 microfarads. This constitutes one element of transmission. And of course, we can propagate either longitudinally or transversely, and we're going to stack these elements up to symbolize and synthesize these 2 forms of waves, and then we're going to get in there with some rather unique detectors and some conventional detectors, and even use our fingers and determine exactly what's going on with these things and see how this correlates with our previous measurements of actual transmission structures and not their analogs. And then we'll finally conclude with some practical applications for these devices in the transmission of electrical energy and industrial scale, and also the use of producing musical sounds and some other things. So we'll move on to our next part here, combining these elements and performing our measurements. So we'll review our test setup here. What we have, we've taken our element that we've shown and compiled these in series to produce on the workbench effectively 31 miles of transverse electromagnetic transmission line. This might be the power line between the substation and load, or it might be a telephone line connecting two towns together. We have our audio oscillator. We have a stereo power amplifier hooked up for mono, and that is our generator, and we've left the end of the line open circuited, so we're dealing with a quarter wavelength similar as before. Now we have a probe for detecting magnetism, and we have a probe for detecting dielectricity. Coming to the workbench here, we have our audio oscillator. We have our power amplifier, which basically this constitutes our generator. Our magnetic detector consists of a thermomilliamp meter that has a small filament in it that gets hot when current flows through it, and then the temperature of this is measured with the thermocouple and produces a scale on the meter. These are usually considered true RMS meters, and our actual sensor here will be a little ferrite loop stick from an AM radio, and that'll pick up the magnetism. What will pick up the dielectricity will be a plasma detector, which is just a little neon bulb in this case. When we go to longitudinal waves, of course, many more possibilities will be happening, but with the transverse neon bulb is about what works. So what we're going to do is find our resonant frequency here. So the probe.
Show the whole transmission line that we're going to test.
Oh, I also want to see our transmission line here. We can get that on the video. There we go.
Step behind it, you can lift it up.
Hold it up. So this is our analog of transverse electromagnetic propagation. You can see the capacitors are in shunt and the coils are in series as shown on the board. And it produces a definite geometric pattern. And of course we've got points where we can make measurement here. Now what we're going to do is determine the resonance, again by measuring the dielectric potential at the end. This time we're going to use the neon bulb rather than the voltmeter. Turn up our power here. And you may be able to hear the thing coming to life. Right about there is our resonance point. Harmonics from the amplifier are interfering with the results a little bit. We also can measure resonance by measuring the amount of magnetism at this end. This actually proves to be a little more sensitive resonance detector. Okay, now with finance we can actually study this wave now and its character. We can probe down the line and see the very characteristic magnetic distribution. So on our first stage here, we have a very measurable quantity of magnetism. Next stage it's dropping off. Next stage is dropping down further until finally we get to the end, there's no more magnetism left. Now with the dielectricity we can start from the end, bring the bulb out of overload a little bit. And we can probe down to the next stage. It's a little weaker. And here it's not even measurable anymore. So the dielectricity has dropped off going this way and the magnetism has gone this way. So we can see our classical distribution of magnetism and dielectricity on a TEM line, where the magnetism rises towards the low impedance source and the dielectricity rises towards the open circuit or high impedance load end of the line. Of course, no load being hooked up at this point. And we also can use our fingers too, which serve as very good measuring devices. The voltages are low enough and the frequencies are high enough. Find the coils at the end here getting quite hot, which can be expected. And then they cool right off until the end, no heat is felt. The capacitors down here are cool. And as we get further down the line, we find the capacitors get warmer. So we find that we have a separation of the heating effect, where the dielectric heating effect, understandably, is occurring where the dielectric energy intensity is maximum, and the magnetic heating effect is maximum at the end where the magnetism is most intense. Now what we'll do next is we'll build up this analog computer into a section of longitudinal magnetodielectric transmission, and we'll compare our frequencies. Oh, by the way, the frequency of this is 1520 kilocycles per second. And we'll compare this with the frequency of our next unit, which will be in our next part here. Okay, our test setup again. We've taken our element and rotated it 90 degrees to give us longitudinal rather than transverse flow, but of course still using the same components in the element. We have our same amplifier. Oscillator arrangement, the amplifier is producing about the same amount of power as before, but now our distributed line looks like this, and it's a quarter wavelength long, meaning that we have our low impedance, high impedance. Now the length that this symbolizes is indefinite by conventional terms because this represents wave propagation in counter space, something that's little understanding of exists. The propagation in counter space would be measured in per mile or per centimeter, so we have to figure our length on that, and so little knowledge exists on that right now that we can't give a definite figure. But we can take precision measurements and determine exactly what's going on here. So right now our oscillator is at 3600 kilocycles. That was our resonance point. I'll put the neon bulb in the end here. Hold our line up so you can see how it's constructed. You can be more careful now because it's much more intense. Transverse than longitudinal mode. Okay, we'll do our sweep here, and you can see the resonance is extremely sharp on this. I just barely move the dial and it goes out, and the activity is so high that now it'll even light a fluorescent lamp with the same amount of power. So as you can see, I only need one wire at this point, where before I had to connect up in conventional electric circuit fashion. And again, reminding you, this is the same amount of power. So we can see the oscillations are much more rapid, much more intense. Now let's study this like we did before. Let's start by seeing what our magnetism looks like. So we'll start down on the bottom here, and we don't get too much indication. And it goes up there fairly well. It's quite intense there. And here I don't even dare bring the thing up, or I'll burn the meter out. So we see, in contradistinction to before, the magnetism is rising towards the open circuit, something that doesn't normally occur with conventional electric waves. Now we'll do the dielectric part. And of course you're probably seeing interference in the TV screen, and of course that's, if you've seen the other videos, is characteristic when we start to deal with longitudinal waves, as they propagate quite well through space. Or in this case we might say counter space. And we can see the dielectricity drops right off. Now for comparison, I'll put the neon bulb right across the line. And you can see it's just brilliant. I don't dare keep it there. It'll be gone in a second. And we get quite a spark off the end of the thing too. So for the same amount of power, this thing is operating at a much more rapid rate, much higher efficiency, and we can do a lot more things with it. And we'll do our heat check again, see where the heat's coming from in here. Feel our input coils, relatively cool. The input capacitors are quite hot. Go down the line here, capacitors are cooling off, but the coils are very, very warm here, this end. So now we have the situation where the heating effect is turned around from where it was before. Now the dielectric input capacitors get hot, and the magnetic output inductors, or more appropriately in this case inductors, are getting warm. So we have quite a few differences here. Now what we'll do next is we'll do some quantitative comparing these differences, and then we'll do a few novel experiments and give some ideas for the experimenter to work with this on his or her own. In reviewing the results of our experiments, we find that the transverse electromagnetic, or TEM wave, produced these following observable effects. We notice that the capacitors, or dielectric inductors more properly, at the input were cool, and at the output were hot. And and the magnetic inductors at the input were hot and at the output were cool. The magnetism piles up at one end and the dielectricity piles up at the other end. We found the oscillations to be rather slow and rather weak. With the longitudinal magnetodielectric, or LMD wave, we found that the magnetic inductors at the input were cool, but at the output were hot. And the dielectric inductors at the input were hot and the output were cool, which is very interesting because the dielectric conductivity was more intense at the output, but that part remained cool. The magnetism and dielectricity piled up at both at the same end. The oscillations were quite rapid, as you can see, by a very significant factor, and the oscillations were strong enough to produce small electric shocks when handling the bulbs, and the bulbs lit up to brilliance way beyond their maximum power handling capability. And both of these tests were done with relatively the same amount of power, about within the range of 15 to 20%. We don't have a high-frequency watt meter to measure this right now. So in comparison, the transverse electromagnetic energy wave, the magnetic and dielectric energies are in space opposition, in that they are at opposite ends of the apparatus. The longitudinal magnetodielectric wave, the magnetic and dielectric energies are in space conjunction, which goes totally against the law of electromagnetism, which says these two energies always must be in quadrature in time and in space, but in here we find that they occur together. And look, comparing again, the TEM, magnetism was hot, the dielectricity was hot. In the LMD, the magnetism was hot and the dielectricity was cool. We can conclude from this and other experiments we've done in the lab previously that TEM, or transverse electromagnetism, which represents basically the form of electricity that we use today in the way that science chooses to look at electricity, is an unnatural form of electricity. Whereas in the longitudinal magnetodielectric, the energy is a natural form, the way electricity naturally wants to exist. And if we go through the old text, we find that dielectricity used to be called electricity and is often still erroneously known as the electric field, which somewhat stands to reason because it's the origins of electricity. Now what we're going to do is we're going to build up an interesting little detector here and show some things that can be done with this network. And one thing I'd like to point out for those that like to build practical things is these networks, the longitudinal magnetodielectric networks, can produce, as was seen, very high voltages and serve as good alternating current voltage multipliers. And without building large Tesla coils or anything with considerable amount of windings on them, you can produce extreme voltages and all the effects that you get with Tesla coils, such as one-wire illumination and bizarre transmissions of interference into the TV camera, and all these things that you normally only see with the Tesla coils. So we find that this analog computer, the LMD wave, is the analog of the most important wave in the Tesla coil, and we can get a lot of the effects that we would normally get with the Tesla coil with this simple coil capacitor arrangement. We find with the TEM, as the dielectric induction builds in intensity, it's always fully across each capacitor, which of course causes the capacitors to fail at the output end, and you can never get high voltages. Same thing with the two-wire transmission line. If you try to get it to resonate, obviously the wires are going to flash over at the output. Where with the LMD wave, the capacitors are all staggered in series, and they're not going to break down due to overvoltage because each one is sharing the load. And that is the important discovery of Nikola Tesla for the production of his high voltages, was the fact that the voltage appeared as a small quantity across each turn and didn't cause flashover between the turns, so produced infinitely higher voltages than was possible with parallel wire transmission lines. The next thing we're going to show is a combination of, you might say, an orgone detector and a Farnsworth multipactor tube connected to this, and show some interesting effects. And then we'll get into a few more practical applications, and that'll wrap this up. Okay, we have a few experiments we're going to do here. We have a 90-volt battery and a Simpson Model 260 voltmeter with a 50 microamp movement, and we've used the range meter as a ballast resistor. And interesting tube is a gas photomultipactor tube that has two photoemissive plates basically facing each other, and then it has a wire in it to basically act as the anode for collecting the emitted electrons for light detection, but we're going to use it for some different purposes here. It has a very slight amount of argon gas in it to reduce the required operating potential. Okay, we have this thing hooked up to a source of LMD current, which is our analog computer, and we'll swing over to the meter here in the photo tube. First, let's take a look at the tube, if we can get it on video, get an idea of its construction. Or actually, I have another one that's partially taken apart, and we can bring this right up to the camera. I've been told these are old balanced photo detector tubes for movie cameras. So you bring it up real close here and we can see what's happening inside. We can focus at that range. There we go, we got it. You can see there's two, well, let's get a little better focus there. There we go. You can see there's two photo plates. Turn the tube around, which are semi-facing each other, which is different than your normal photo tube construction because usually you only have one plate. In this case, the anode wires are in the back, and those are photoemissive surfaces too.
Why don't you bring the thing way up into macro here? Bring it way up close here. Still won't focus. We're in the macro.
There we go. Take a look at the inside of this. See, there's the two silver cesium plates, and then the anode wire is barely visible. It appears more as a shadow, but there's two anode wires basically right there that go up to collect off of these plates. So it's a completely balanced arrangement. We're using this as a Farnsworth multipactor tube, and the anode wires typically are not used except for as a remote source of excitation. So we'll go back over to the setup here. Now, we've been doing a lot of experiments to build a detector of bioenergetic fields, or what some people would call an orgone detector. We haven't done anything solidly conclusive yet, but nevertheless we are getting readings and responses. So the apparatus is brought to a power level to keep this thing operating at the necessary threshold. I can pick this photo tube up, and of course when I shine the light on it, it tends to move around and respond. But when I put my hand on it, you see the meter jumps right up. So we're getting close to what we want here. We have to work more with thresholds and build our own tubes, but of course we're working all with junk parts. By the way, these parts are all found at ham fests and in surplus stores and garbage cans, and sometimes you can find the stuff laying in the middle of the street if you're lucky. Now what we're going to do is change our setup here a little bit. Connect this as a regular photo tube and remove our source of excitation. And if we can see, the Simpson shows that we got a slight response from the fluorescent lamp.
You're right in front of the meter, so I can't show both.
There we go. We got a little bit of response from the room illumination, which is pretty bright for the videotaping purposes. Now I'm going to bring the intensity of our apparatus up here to a point where we get some reasonable output. And we can see that the phototube responds quite readily to the longitudinal dielectric induction existing at the end of this, primarily due to the presence of ionized gas. Get behind here so you can see the meter. See, it just jumps right up. Even though the illumination by the gas in there is barely visible, and of course I have a big 750 watt bulb hanging right up there on the ceiling, and that produces hardly any output at all. Now we'll go back to the board and do a little brief description of what multipactor action is all about. This was something discovered by Philo Farnsworth around 1930. He developed a whole series of tubes based on this principle that eventually led to practical nuclear fusion. Totally electronic, required no large magnets or lasers, and the thing basically occupied a space of roughly 10 cubic feet and produced 100 kilowatts of direct current, 1 ampere, 100 kV, for about 5 minutes before the little electrode screens inside the tube would melt. Going back to the original photo multipactor, what happens is something will dislodge an electron from the plate, which will fly off and then be attracted to the other plate. the little high-frequency oscillations of the wiring will produce jittering. Now this electron flies off, hits the other plate, will knock more electrons off, which will fly around and go back to the other plate and knock more electrons off until eventually you can build up very powerful UHF oscillations with these things. The reason Farnsworth developed this tube was at the time the tetrode vacuum tube had not been developed yet. And being Farnsworth was in the process of inventing television at that time, he needed very high gain, high impulse response, or you might say wide band amplifiers, and he just couldn't get that out of the old triodes. So he decided to abandon the hot cathode grid tube completely and came up with this photo multipactor tube, which now in its final form that's available to us today is known as the photo multiplier, which many people are familiar with and forms the heart of every television camera. Television camera tube, of course, being invented by Father Farnsworth, as many know. Our dielectric induction detector was basically this down here, using this multipactive process to provide roughly a gain of about 60 to 70 decibels, so that the slight amount of ionization produced by the induction produced a significant response on the meter. Now, of course, we hook this to a tank circuit tuned to the appropriate transit time frequency. This effect will be magnified even more, and gains of 120 decibels are possible with a single tube. Now we'll get into some maybe practical connections of this circuit and a few other things, and that'll be pretty much it for this demonstration. So we have a few things here to consider and possibly experiment with. Now in industrial electricity, we have a situation where if we have a large system of motors, which require, of course, electrical energy and magnetizing energy, that the magnetizing energy and electrical energy have to be transmitted through the TEM line to the motor, resulting in two waves which tend to overheat the lines and drop the voltage. And normally what's done is a dielectric inductor or capacitor is hooked across the motor to provide the magnetizing energy, because capacitors will generate magnetizing energy, and that relieves the transmission line of the duty. And further, the magnetic induction, which is the prominent element in most transmission lines, being that the voltage doesn't operate much above your low voltage points, usually less than 66 kV, which most feeder lines are, you don't have enough dielectric induction for them to be anything more than an inductance coil. So it's just like a big transformer winding. The capacitor will resonate with this magnetic energy in the wire and cause the voltage of the system to raise as you go to the load, which of course is quite different than in normal DC circuits. So it's not uncommon in an alternating current power system that the voltage will start off nominal at the generator, which is usually 13.2 kV, and go up to 13.8 or 14, and if you remove the motor, it would go up to infinity. What happens when this is done, when the voltage gradient raises at the plant, the kilovolt ampere reactive hour meter will start to turn backwards, which usually causes trouble with the power company. Okay, now there's a new way to correct this, and we haven't performed all the experiments yet, but we're just starting on this. It's kind of hard to work with large power lines and factories and stuff like that, because usually they don't want to give you permission to go in and monkey with their stuff, not alone getting it to conform to the National Electric Code. But in other countries, of course, it's possible to do this without the restriction. And laboratory analogs can be built up the whole way, and it can be completely computed on the workbench. So in this case, what we do is build an LMD analog which conjugates or is in conjugation with the TEM transmission line to neutralize the transmission effect completely, rendering the motor and generator as one apparatus. Now this is still a theoretical type of situation, but nevertheless our mathematical and physical studies show that it's quite possible to do this, and we're getting ready to perform these experiments, and of course the information will be released in video and written form when we're done. Another thing is an LMD network is an analog of an organ pipe, and it will produce a complex harmonic spectrum rather than a single sine wave frequency that you conventionally get out of the LC oscillating circuit, or again the single repetition rate frequency that you usually get out of your RC networks, which contain harmonics that usually are not what you find in natural musical instruments. So a negative conductance, which may be a cathode follower with a capacitor in its cathode, or the capacitance of the line producing negative transconductance and oscillations. It could be a Hartley oscillator. It could be a photomultipactor tube. There's many different ways to produce negative conductance or resistance. This is connected to one end of the line to maintain the harmonic oscillations in the line. And then the dielectric end is very lightly coupled to an amplifier, which of course produces the sound in the speaker, and your musical keyboard, of course, would switch these things in as necessary to produce the music. So these are some things that the experimenter and the industrial engineer can consider in using these things for practical advantages, and of course they do produce very high voltages and Tesla coil effects without the high frequencies and interference with other services, which of course would get one in trouble with the FCC. So that wraps up our presentation of analog networks and the comparison of transverse and longitudinal energy flow in general. And I'll turn you back over to Tom Brown, Director of Borderland Sciences, to give a conclusion on our...
Thank you, Eric, for that very practical demonstration of the difference between transverse and longitudinal waveforms. Something that you've brought to the lab bench, and now we can understand it in very real forms, and the experimenters around the world can try these things for themselves and thereby carry on the works of Nikola Tesla, Charles Steinmetz, Philo Farnsworth, and of course yours, Eric. We must point out here, Eric, that on this date here, January 25th, 1988, here we see Eric going to cloud of dust. He's been found in violation of the universal speed limit of 186,000 miles per second. But as we know, this speed limit has been set by modernistic science, which has gone into realms of abstraction far beyond the practical realities of actual work in the lab. So we just want to thank you for watching, and we wish all of you out there good day and good science.